Tonight, what we're going to be talking about are how to draw basic covalent compounds using the Lewis dot structure method. And so the very key to understanding how to draw the basic covalent compounds, and first let's review, covalent means that these are sharing the electrons. So they have a total number of electrons and every element's going to be sharing them to make everybody as happy as possible. And so what you're going to need to do is count the number of valence electrons that each can contribute, and then in the end everybody has to have their full happiness of being an octet. Okay, so these are the various steps that you need to write down in order to draw a covalent Lewis dot structure. And so first you need to count the number of valence electrons for each element and then add them up, and that's how many total electrons you can account for. Then what you want to do is draw an arrangement of the atoms. And we're going to be talking about compounds like CH4 or CO2, NH4 plus, things like this, and you're going to have to figure out what is the best structure, how would they combine to form these bonds. So they kind of have some hints, and the first is that you always put the least electronegative element in the center typically. So that means that carbon is always in the center. Hydrogen is always on the outside. Okay, why? Because it can only form one bond. Why can it only form one bond? Because it only has one valence electron. So it only has this opening that it needs to fill. It does not have all of these other sides that it also needs to fill up like every other element. So hydrogen's kind of a little goofy. Halogens are also on the outside, or almost on the outside. As you get further on in the rows or periods, you can have what we call as an expanded one, but halogens typically only form one bond, and that's why they always have to be on the outside. So F, for example, only has this one opening right there, so it's going to only form one bond, therefore it has to be on the outside. And then what you want to try to do is make it as symmetric as possible, but what we don't do in this class is form little circles. So it's not going to be like this guy is connected to that guy, which is connected to that guy. So you're not going to form circles or triangles or anything like that. They're going to form linear structures. Okay, then what you want to do is you want to connect all atoms using single bonds, and then you want to, for every remaining electron that you got from the total valence electron count, what you're going to do is you're going to fill in, this should be the octets of the outer atoms, which means you're never going to fill it in for hydrogen. Then if there are any leftover electrons, you're going to place them in pairs on the central atom. And then what you're going to do is make sure that everybody's happy. So from that, you're going to fill in double bonds and triple bonds, possibly using lone pairs from the outer atoms. These steps don't make a lot of sense until you actually start doing them. So let's try to do one. So steps for drawing. First, you want to count the number of valence electrons for each element. So bromine has 7 valence electrons, but we have 2 of them. So total, we have 14 electrons we can deal with, which means I can draw 7 lines. And I'm going to typically draw structural structural ones as opposed to Lewis dot structure ones. The only difference is that instead of drawing dots, I draw a line. So each one of my lines represents a set of 2 electrons, whereas if you look at other ones, they might have dots, which represent 1 electron each, or if you have 2 of them, that would obviously represent 2 electrons. So next, we need to draw the arrangement of the atoms. Because there's only 2 elements, there really is not going to be a center atom. So we've got 2 BRs drawn. Connect all atoms using only single bonds. So we're going to put a single bond there. And then it says using the remaining electrons. So far, this represents a single bond. Okay, why is it a single bond? Because you only see one line. And that represents the use of 2, I guess I should try a different color other than blue, 2 electrons. Okay, so we had a total of 14 and now, or 7 lines, and so now I've used 2 electrons or 1 line, so I've got a total of 6 more lines that I can do. So what it says is using the remaining electrons, fill in the octets of the outer electrons. So what you're going to do is 1, 2, 3, 4, 5, 6. So I have used up 6 other lines in order to make all of these guys octets. And what an octet is meant by is you have 4 lines, or I guess that's a total of 8 electrons. And even though these electrons are being shared, we count them on each of these guys. So this bromine has 2 of those electrons, and that bromine also has 2 electrons when you're doing your counts. So if there are any leftover electrons after step 4, which we don't have any because we had 14 and we used up 14 to draw this, and we don't even have a central atom, we're going to kind of skip this. And then we need to fix any problems by making double bonds. Well, ours is extremely happy because if we relook at our finalized structure, which is Br, single bonded to another Br with these 3 lone pairs. These guys represent a lone pair. Why? Because they are by themselves, and there are 2 of them. These represent shared electrons because they're being shared between this bromine and that bromine. So if I look at my final structure, I need to make sure that everybody's happy and that I only use my 14 electrons that I had accounted for, which is 7 lines. So counting off, I'm going to go 1, 2, 3, 4, 5, 6, 7. So as far as total electrons, I've used up all the right ones. And then as far as electrons go for each one, we have 1, 2, 3, 4, which represents 8 electrons, or 1, 2, 3, 4, which represents 8 electrons. So everybody's happy. So this is my finalized structure for Br2. Now let's try NCl3. So counting, N has 5 valence electrons, Cl has 7, but we have 3 of them, so it's a total of 21. So 21 plus 5 is 26, so I can use 13 lines. Okay, so let's try to draw the arrangement. Typically, it's going to be the first element is the least electronegative, so I'm going to put N in the center, and I'm going to surround it with my Cl's, try to make it as symmetric as possible. This, you can see, is kind of like a mirror image. Now it says connect all atoms with only single bonds. So 1, 2, 3 single bonds. So I've used up 3 out of my 13 lines. Using the remaining electrons, fill in the octets of the outer atoms. So right now I only have 2 electrons on each of my outer atoms. So I'm going to draw in 3 more to make it have 4, which means it's an octet because it'll have 8 total electrons. Okay, so now counting, I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used 12 lines. So in step 5, if there are any leftover electrons, well, I needed to use 13 and I've used 12. Okay, so I have 1 extra, place them on the central atom. So I'm going to put it right on that end. Now I need to fix any problems by making double bonds. Well, by problems, it means that not everybody has their octet. So looking at this, everybody has the octet. Now nitrogen has 4 lines attached to it, which means that it has 8 total electrons, which means it's happy. So this is my finalized structure. Okay, the last one that we're going to be doing tonight is CO2. Counting all my valence electrons, carbon has 4, oxygen has 6, but we have 2 of them, so that's a total of 12 plus 4, so 16 total electrons, which means that I have 8 lines I can draw. So I'm going to draw the arrangement. You try to make it as symmetric as possible, putting carbon in the center. Typically, the first element is always going to be in the center unless it's hydrogen. Then it'll be on the outside. I'm going to surround it by my O's. Connect all atoms using single bonds. Okay, now using the remaining electrons, fill in the octets of the outer electrons. So I have 8 lines, so I have 6 more that I can do. So I'm going to 1, 2, 3, 4, 5, 6. So all my oxygens are happy. The problem is there are no leftovers, so I can't place any lone pairs on that carbon. So I'm going to skip to number 6. Fix any problems by making double bonds using lone pairs from outer electrons or outer atoms. So if I look at this carbon right now, I only have 1, 2 lines, which means it is not an octet. So what I need to do is I'm going to borrow or take one of these lone pairs and kind of donate it to that guy. Okay, and that now, if I redraw it, would look like this. Okay, I've still used only 8 lines. Okay, but this carbon's still not happy. So what's going to happen is it's going to try to borrow another one from that oxygen. You try to make it as symmetric as possible. Usually if you borrow from one, you're going to borrow from the next one. You're not going to take another lone pair, and we'll get more into that in a later unit or later in this unit. You're not going to try to do that because they're going to try to be as symmetric as possible. So if I did that, then what I've got is I've got O with 2 lines and 2 lines there to that carbon, and now this carbon to that oxygen is 2. In that. Now, just to let you guys know, those guys are known as double bonds. Why are they double bonds? Because you have 2 lines in between 2 elements. If there were 3 lines, so let's say it was like this guy right here, this would be known as a triple bond. So it's exactly the way that you would think of with baseball. You've got single, double, and triple. Okay, so trying to just go over this again, we have a total of 16 electrons or 8 lines I can draw. So I've got my finalized structure looks like this. Now you want to make sure that everybody's happy. So once again, I can only use 8 lines, which I recount 1, 2, 3, 4, 5, 6, 7, 8. Good. And then I want to make sure that everybody's happy. This action is 1, 2, 3, 4. This other action is 1, 2, 3, 4. And the carbon has 1, 2, 3, 4. So everybody's happy. So this is my finalized structure. All right, then we're going to just talk about those bonds a little bit more. So a single bond has 2 electrons. How do you know it? It's going to have one single line because that represents 2 electrons. A double bond will be sharing 4 electrons, which represent by 2 lines going in between. So that's 4 electrons. And a triple will have 3 lines going in between 2 different elements. Okay, as far as relative strength, it kind of makes sense that the single bond would be weakest and then up to the triple would be strongest. Think about somebody going over a cliff, and this represents you'd have 1 arm, and this would represent 2 arms, and this would represent 3 arms. So which one would form the strongest attachment or strength of the bond? It would obviously be the one with the 3 arms, so therefore the triplet is the strongest. What's interesting to note is that actually as you get stronger, you get shorter. So not only does it get stronger, but they actually get closer together. So if I were to represent a single bond as this, a double bond would be, let's say, this, and a triple bond would be a lot closer yet. So it would actually get even closer and closer to each other. All right, hopefully you have kind of an understanding of how to draw a basic covalent structure, and we'll be practicing more of these in class.